Testing, can you hear me? Testing, can you hear me? Alright, so I'm going to be learning about data structures and algorithm again. So last stream, I learned about Dijkstra's algorithm. I learned about minimal cost spanning trees. I'll tell you what my understanding of Dijkstra's algorithm is. So from what I understand, let this load. Yeah, I don't know when this is going to load. So last stream I learned about all this, and then this stream I'm going to be learning about sparse matrix. This loaded. What's wrong with this? Okay, let's say we have this over here. So in Dijkstra's algorithm, you need to find shortest path from the starting point, let's say A, from every other point. Shortest path from A to C, A to D, A to B, A to F, A to E. So there will be a vector D. There will be an array. It's called D, and then D. It will D. The array D will store all the things, all the shortest path. So let's say we have this is vector 0. Oh, no. So 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 6, yeah. So D 0. So this is the first vertex. And let's say we are starting from A and going to every other vertex. So D0 will at the start be 0. So first, hold on. This is the vertex and D. So initially D will be infinity for all of them. Let's call it, yeah, infinity for all of them. And from D, from A, we will visit every path, and if the cost is lesser than the current value, then we replace the current value. So for example, currently it's infinity. When we go to C, 7 is lesser than infinity, so we replace infinity with 7. And then if we happen to come across that path, let's say there's F over here. So if we go A, so C, P, no wait. Yeah, C, F, the cost is 7 plus 2. And if we go A, C, D, F, cost is 7 plus 2, plus 1 plus 2, which is 10. So D for this vertex is initially infinity. If we do A, C, D, F, then the cost is 10. 10 is lesser than infinity, so this should be replaced by 10. If we do A, C, F, 7 plus 2 is 9. 9 is lesser than 10, then the new value for this will be 9. So what Dijkstra's algorithm does, that A, the first vector is initially 0. So first set all of them to infinity and then set the first one to 0. Set the first one to 0. And we also mark whether each vertex is visited or not. So these are vertex. And we also mark them as visited or not visited. So initially they are all not visited, but then initially they are not visited. But when the algorithm starts, let's see the algorithm. When the algorithm starts, we give a graph and we give the integer s. The shortest path distances will be stored in D. So we start with S. In my example, S is A. So D 0. So D of A, shortest path to A will be set to 0. This is the first thing. And then the next thing is A will be marked as visited. So A will be marked as visited. And then for all the children of C and E, since we travel there, where is all the cost stored? G. Oh, there's a weight property. Okay. So the weight from A to C is 7. So, okay, so the current minimum D value is 0. So A0 is 0. And then 0 plus 7 will give us 7. So the cost of reaching to C is 7. And 7 is replaced by infinity. So if I copy this, how do I only pick the... So this is 0 and then this becomes 7. And for this child, E, so E is in this position, E becomes 9. And then after setting these two, after setting the distance for the children, we then visit the child with the smallest cost. So we visit this 7 over here. So we visit C. Now we set uh, the distance of all the other vertex. So C, the current distance is 7. 7 plus 5 is 12. So B is 12. I made a mistake here. 7 goes to C. And then B is set to 12. And C to D, so 7. So currently it's the distance to C is 7. And then 7 plus 1 is 8. So distance to D is 8. And then distance to F is 7 plus 2, 9. Over here, it's 9. 7. And now We pick the shortest path among the children of C. So B is 12, D is 7, F is 9. So next, oh yeah, and we mark C as visited. So A is already visited. We set the distances for C and E, and then we visit C. So C is visited. And now from the shortest path among these three, we visit the one with the shortest path, and that is F. Right? No, D is 8, A, B, C, D, E, F. So D is the shortest. Yeah, we visit D. And then from D, which is 8, plus 2 is 10. D to F is 10. But the shortest distance stored over here is 9. 10 is not smaller than 9, so we don't replace this 9 over here. And we then visit F. We visit the smallest child. We visit the child with the smallest distance, which in this case is F. No, I don't think we visit the. Do we? No, I don't think we do. It's a recursive function, so when it unwinds back, we come back to C, and then we go to the next smallest child, like the child with the smallest distance, and it's F. Then we mark F as visited, and then unwind visit this next. No, F, and then F. Currently, it's 9. 9 plus 6 is 15, but 15 is larger than 12, so 12 doesn't get replaced. So that means we unwind, and then we visit the next child, which is B. So then B gets visited. But B is the end. It has no like out degree, right? So we unwind. We already visited all the children, so we unwind again. Next, we visit E. We visit the next child, and then E to F is 10, but 10 is bigger than 9. So 9 does not get replaced. Then we unwind, and the entire recursion finishes. So we go out of the function. And this over here is what we are left with. This over here is what we are left with. So let's see. We have this function over here. Yes. It prints everything in one line. How do I break it up? I don't like this. Should I just take a picture? Right, so Dijkstra's algorithm. Also the minimum vertices. Copy. Paste. Okay, so first over here, node count, set all of them to infinity. So D is inputted. And then all of them are infinity. And then DS, S is like where we are starting from. In this case, it's A. So wait, S. I'll just write it here. A, B, C, D, E, F. And then this is set to 0. And we enter this for loop, you're going through all the vertices from I to node count, basically all the vertices. V is equal to minimum vertex GD. Wait, first all of them are not marked as visited. Visited, this mark is not a separate array. I'm just representing a separate array over here for simplicity, but visited is like an internal property, I think. Set value, yeah, this. Set value, V visited. But I I think it should be an internal array, I think. Anyways, so initially they are false, the visited values. And we have to select the minimum vertex. So how do we select the minimum vertex? So we initialize V from all the count, we process all the vertices. And the moment we find a non-visited one, so for example, the first A, we set the value for the distance, but it's not marked as visited yet. It's not marked as visited for all the vertices. So this V is set to I. So V is 0. 0 represents the A index. Then break for process all the vertices again. Get value. So if it is not visited and di is less than dv, then v is equal to I. Okay, if it is not visited and di is equal to dv, v is equal to I. Oh, I understand what they're doing. Or maybe not, I don't understand. Maybe in later, like if it's like half done, then I might understand. Anyways, they return v. V is set to A, right? 0 is less than dv. So none of these are visited. di. dv is 0. Distance to vertex I. So infinity is less than 0. That is false. So v value doesn't change. Yeah, so v gets returned. And then, so v is A, and then v is set to visited. V is set to visited. So minimum vertex, it selects the vertex with the minimum cost. In this, like currently it's A, but once they start getting into more detail, I think I will have a better understanding. So we visited. If it is an infinity, so if A is okay, let's just skip this part for now. Integer and list g neighbors p. So now g neighbors, we list out the neighbors. I think the neighbors function only lists out the out degrees, only C and E. It doesn't list out the vertex coming from, doesn't list out the from degrees, right? The from vertex, only two vertex. Anyways, we loop through the quote unquote children. Well, actually, it's the next path. We loop through the next vertex, and then W. Okay, so let's say it's C. W is C. And then dW is more than dV. So the distance, the currently set distance is more than 0. Currently set distance is more than 0 plus 7. Because later down the line, we take this distance plus 2. So right now we are doing 0 plus 7. Then we get the distance of this. So if the currently set distance is more than the new possible distance, then we set the new distance. That sounded confusing, but you get the point. Same thing for E. Currently set distance is more than 0 plus 9. So we rewrite the value to 9. Sorry, this. And then what? And then, okay, we are looping through the next vertex. So before it was vertex I, which is A. Now it's vertex 2, which is B. Vertex 2, which is B. I don't like how the loop is done. Shouldn't it be A first and then C and then B? Why is it going A to B? Anyways, if it's B, if the next one is B, then we choose the minimum vertex. Minimum vertex. So anytime we shouldn't set this as visited. Find the next closest vertex. So B is unvisited. So V over here will be B. And node I, if it is not visited, so this is visited, this is not visited, and DI is less than DV. DI is less than DV, that is false. So 0 is less than infinity. No, it's not visited. Infinity less than infinity, that is false. 7 less than infinity, that is false. Infinity less than infinity, that is false. So none of these are true. No, 7 is less than infinity. So 7 is chosen next. So V is equal to C then. So this loop finds the smallest value among this array. Smallest value of the unvisited vertex. Okay, so minimum vertex finds the smallest value of the smallest distance of the unvisited vertices. Infinity, 7, infinity, 9, infinity. So we chose 7. So we are choosing C next. C, we then choose 5. So we set value to visited. And then if dB is infinity. Like, how is this possible? How is this dB is infinity? Let's say there's another array, E, F, G, which is like isolated from the rest of the graph. So let's do G. Now, this is just for the sake of understanding. Anyways, let's just skip this line for now. So endless G neighbor, so B, D, F. And then going through this. So first of all, B. So weight of B is more than, okay. So current weight of C, which is over here, current distance of C, which is 7, plus this weight, so which is 5. So from C to B is 5. C to B is 5. So infinity is more than 7 plus 5. This is true. So dW is equal to, so dW now found a new minimum, 7 plus 5, which is 12. Now going to through next, 7 plus 1 is 8. So D, 8 for D. 7 plus 2 is 9. And then we go find minimum vertex. So out of all the unvisited one, out of all the unvisited one, we find the smallest value, right? The smallest di value, which in this case is 8. So 8 plus 2. No, we first set it to visited. Set it to visited and then neighbors and then set the new value, new possible value of neighbors. So 8, 8 plus 2 is 10, but this condition will be false. So then we choose the next minimum vertex. So out of all the unvisited values, we will choose 9. Yeah. Okay, this loop over here chooses the smallest value. If the values are the same, it chooses the latest value, right? Because you're still looping through it. Even if it chooses E, it's still looping through it. And then, wait. No, I think it will choose E. That is correct. It will choose E. And then 0. So mark it as visited. And then neighbor of E is F. 9 plus 1 is 10. So D of F does not get reset because 9 is smaller than 10. So then next, going back to this loop, the next vertex would be, the next smallest unvisited vertex would be 9. 9 is now set to visited. And then it has no neighbors. So anyways, next smallest vertex is this over here, 12. Mark it as visited, but it has no neighbors. And then the next vertex, okay, so now we are at with G. So as soon as we find a not non-visited vertex, we break out. So we end up with G. And then if G is not visited, so this will never be true. So this function returns this vertex, which is G. Since G is infinity, return because unreachable. Yeah, what do you mean return? Do we like, if there are some unreachable nodes, do we just return? So we assume that all the visited nodes are fully complete. So anyways, we end up with this. So now I understood these two algorithms. Also, there's this other one called the minimum cost spanning tree. It's like Dijkstra's algorithm, but it takes the, instead of dv plus weight, it's just the weight. So get rid of this. Get rid of this. So minimum cost spanning tree, what this corrects is that, for example, with f we have 2, 2, 6. The value of f will be 2. Actually, it will be 1 because 1 over here. It's 2, 2, 1, not 6. B is 5, 6. So B will be 5. A will be, there's nothing going into A. A will be 0. E will be, C will be 7. E will be 9. D will be 1. 9, 1, G infinity. Let's forget G. So if we follow this, like let's say 0 and then 7, 1, 9, we get a tree. We basically get a tree. 1, 5, 1. where all vertex are visited and the sum of their cost is the minimum. The sum of their cost is minimum. This is the minimum cost spanning tree. But over here, they didn't do 9. Oh, sorry. Minimum cost spanning tree is for undirected graphs. So this 9 wouldn't count. So when it did neighbors, so G neighbors, when we are at F, E will count as a neighbor. Oh, it's undirected graph. Sorry. Undirected graph. So let's assume there are no arrows over here. So 7, 1, 2, 1, 5. So this is now converted to this. Prim's algorithm. Set it to infinity, 0, visited. You have this function over here. Add edge to MST, minimum cost spanning tree. We're adding an edge. And then this is the change. We have a wholly index for vertex that is i's parent in the MCST. Anyways, now on to the actual topic I was trying to study. Sometimes we need to represent a large two-dimensional matrix where many of the elements have a value of 0. Typical situation arises when the vast majority of values stored in an n times m matrix are 0, but there is no restriction on which positions are 0 and which are non-zero. This is known as a sparse matrix. One approach to representing a sparse matrix is to concatenate the row and column coordinates into a single value and use this as a key in a hash table. Thus, if we want to know the value of a particular position in the matrix, we search the hash table for the appropriate key. If a value for this position is found, it is assumed to be 0. This is an ideal approach when all queries to the matrix are in terms of access by specified position. However, if we wish to find the first non-zero element in a given row or the next non-zero element below the current one in a given column, or recover all of the non-zero values in a given column, then a hash table requires us to check sequentially through the entire table. Another approach is to implement the matrix as an orthogonal list. Consider the following sparse matrix. The corresponding orthogonal array is shown in the figure. So columns. So 0, 0 is 10. Why is it so pixelated? 0, 1 is 23, and then 0, 6 is 19. Here we have a list of row headers, each of which contains a pointer to the matrix records. Second list of column headers also contains pointers to matrix records. Each non-zero matrix element stores pointers to its non-zero neighbors in the row, both following and preceding it. Each non-zero element also stores pointers to its non-zero neighbors following and preceding it in the column. Thus, each non-zero element stores its own value, its position within the matrix, and 4 pointers. Non-zero elements are found by traversing a row or column list. Note that the first non-zero element in a given row could be in any column. Likewise, the neighboring non-zero element in any row or column list could be at any higher row or column in the array. So we also have pointers going to one above and one below. Thus, each non-zero element stores its own value, its position within the matrix, and 4 pointers. So one above, one below, one to the left or right. Okay. What exactly should be stored in various non-zero cells of the sparse matrix depends on the application. In some cases, knowing the row column locations for individual cells is important. For example, if you want to normal operations on matrices, such as adding two matrices that are stored using the sparse matrix representation, then it is an important part of each cell comparison to know where there's a typo here, where exactly we are in the array, any natural traversal of the arrays. Thus, each non-zero element would store its row and column position explicitly. To find if a particular position in the matrix contains a non-zero element, we traverse the appropriate row or column list. Example, when looking for element at row 7, column 1, and traverse the list either for row 7 or for column 1. Traversing a row or column list, if we come to an element with the correct position, then its value is non-zero. If we encounter an element with a higher position than the element we are looking for is not in the sparse matrix. In this case, the element's value is 0. For example, when traversing the list for row 7 in the matrix of the figure, we first reach the element at row 7 in column 1. If this is what we are looking for, then then the search can stop. We are looking for the element at row 7 column 2, then the search proceeds along the row 7 list. For each to next reach the element at column 3. At this point, we know that no element at row 7 and column 2 is stored in the sparse matrix. Okay, so from the 1, 0, 1, 3, row 7, 1, 3, there is no column 2. In some applications, a given row or column represents a vector of information about some objects. For example, consider if you want to store a database about review ratings of movies. There are a lot of movies and a lot of reviews on the database, then no reviewer will have reviewed a significant fraction of the movies. No movie will have been reviewed by significant fractions of reviewers. So sparse matrix representation might be ideal when each column stores the ratings information for a given reviewer. Each row stores the ratings information for a given movie. This allows operations like finding all reviewers by a given reviewer. However, which column a given movie is in is arbitrary. In this case, each non-zero cell of the sparse matrix might need to store reference to its rows and column headers. The cells probably do not need to store meaningless row column numbers. Insertion and deletion can be performed by working in a similar way to insert or delete elements within the appropriate row and column list. Each non-zero element stored in the sparse matrix representation takes much more space than an element stored in a simple n by n matrix. When the sparse matrix is more space efficient than when is the sparse matrix more space efficient than the standard representation? To calculate this, we need to determine how much space the standard matrix requires and how much space the sparse matrix requires. Size of the sparse matrix depends on the number of non-zero elements. N and Z. While the size of the standard matrix representation does not vary, we need to know the relative size of a pointer and data value. For simplicity, our calculation will ignore the space taken up by the row and column header. I don't think we should ignore these ones, row and column header. As an example, assume that a data value, a row and column index, and a pointer each require 4 bytes. An n by m matrix requires 4 n by m bytes. 4 n m n by m matrix requires 4 n by m bytes. How though? Oh, you mean, so what is this called? A sparse matrix. This is called a sparse matrix representation. This is called a standard. No, this is a sparse matrix. What is this representation called? Okay, so in the first representation, it is 4 times n by m, right? Because 4 bytes for a data value, and there are n times m of them. Sparse matrix requires 28 bytes per non-zero elements. 28 bytes per non-zero elements. 4 pointers, 2 array indices, one column, and one data value. So 4 plus 2 plus 1 is 7, and each takes 4 bytes. So 28 bytes. If we set x to be the percentage of non-zero elements, we can solve for the value of x below which the sparse matrix representation is more space efficient. Using the equation 20x is equal to 4mn, solving for x, we find that the sparse matrix representation using this implementation is more space efficient when x is less than 1 over 7. X is the percentage, right? So 28 divided 4 divided by 28 is 1 over 7. That is, which is less than about 14% of elements are non-zero. Different values of relative sizes of data values, pointers, and matrix indices can lead to different break-even points for two implementations. Time required to process a sparse matrix should ideally depend on NNC searching for an element. The cost is the number of elements preceding the desired element on its row or column list. Cost for operations such as adding to matrix should be theta and m in the worst case when one matrix stores n non-zero elements and the other stores m non-zero elements. Another representation for sparse matrices is sometimes called the Yale representation. MATLAB uses similar representation with the primary difference being that MATLAB representation uses column major order. Scientific packages tend to prefer column-oriented representation for matrices since this is the dominant axis need for operations to be performed. MATLAB representation stores a sparse matrix using 3 lists. First is simply all of the non-zero element values in column major order. 10, 15, 20. Okay. Column major order. 10, 45, 40. And 45, 40. Oh, I see. Then the next column. 23, 5, 32. And the next column. 93, 12. The second list stores the start position within the first list for each column. 0, 3, 5, 5, 5. 0, 3, 5. The third list stores the row positions for each of the corresponding non-zero values. Okay, row I understand. 10 is at row 1, row 0, row 1, row 5. 0, 1, 2, 3, 4. No, 40 is at row 4. Yeah, 40. 40 is at row 4. I don't understand this. 0, 3, 5, 5, 7, 7, 7. So column 0. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6, 7. What is the second list store? Oh, I understand. So then the first column starts at position 0, 0, 1, 2, 3. Next column starts at element 3. And then 3, 4, 5, 5, 8, 0, 1, 2, 3, 4, 5, 6. Oh, the next column starts at element 6. Why does it say 5? 0. I think that's wrong. Second list stores the start position within the first list for each column. 0, 3. Start position within the first list for each column. 0, 3, 5. If the matrix has C columns, then the total space required will be proportional to C plus 2 non-negative integers, non-zero elements, number of non-zero elements, number of non-zero. This is good in terms of space. It allows fairly quick access to any column, allows easy processing of any non-zero values along a column. However, it does not do a good job of providing access to the values along a row. It's terrible when values need to be added or removed from the representation. Yeah, what I don't understand this column start. The second list stores the start position within the first list for each column. Start position within the first list. So 0. So in the first list, start position is 0. 0, 1, 2, 3. Next start position is here. 0, 1, 2, 3, 4, 5. Next start position is 32. But that's wrong. Next start position is 93, not 32. 0, 1, 2, 3. What if it's going in reverse? 0, 1. No, never mind. Never. I think. Okay, never mind that. Skip list. I will read this and then I will end the stream. This module presents a probabilistic search structure called the skip list. Like the PST, skip lists are designed to overcome a basic limitation of array-based and linked list. Either search or update operations require linear time. The skip list is an example of a probabilistic data structure because it makes sense of its decision at random. Makes some of its decisions at random. Skip list provides an alternative to BSTs and related tree structures. The primary problem with the BST is that it may easily become unbalanced. The 2-3 tree is guaranteed to remain balanced regardless of the order in which data values are inserted, but it is rather complicated to implement. The AVL tree and the split tree are also guaranteed to provide good performance, but at a cost of added complexity as compared to the BST. The skip list is either to implement and then is easier to implement than non-balanced tree structures. The skip list is not guaranteed to provide good performance. And good performance is defined as theta log n, search, insertion, and deletion time in the worst case, but it will provide good performance with extremely high probability. As such, it represents a good compromise between difficulty of implementation and performance. Here we illustrate the skip list concept. A skip list can be viewed as a sorted list with some extra pointers. We start with a simple linked list whose nodes are ordered by key value. To search this list requires that we move down the list one node at a time, visiting O n nodes in the average case. Now consider the effect of augmenting the linked list with additional pointer at every node. If we add a pointer to every node, that lets us skip alternate nodes, alternating nodes, cutting the work roughly in half. So we are talking about sorted list, right? Oh, okay. Okay, so we can check the value of 25. We can check the value of 5. We define nodes with a single pointer as level 0 skip list nodes. The nodes with 2 pointers as level 1 skip list nodes. Or level 0 skip list, level 1 skip list. And let's find the node with the value 62, or we first check 5 and 25. And then we move to 25. We check 30, 31, move to 31. 25, 31. And from 58, we move to 62. You can extend this concept, making deeper nodes to skip greater distances in long list. The ideal skip list will guarantee O log n search time by skipping halfway through the list on the first step, quarter on the second step, and so on. Searching for the key 62 starting at deeper level. Okay. We can continue adding pointers to selected nodes in this way, giving a third pointer to every fourth node, giving a fourth pointer to every eighth node, and so on until we reach the ultimate log n pointers in the first and middle nodes of the list, or a list of n nodes. With this arrangement, the worst case number of accesses is theta log n. We store with each skip list node an array named forward that stores the pointers. Position forward 0 stores 11 0 pointer. Forward 1 stores level 1 pointer, and so on. It also uses kvpay to store key and record for the node. Skip node class is as follows. Got a value. Forward new skip node. Each skip list node an array named forward that stores the pointer. Position forward 0 stores level 0 pointer. Position forward 0 stores this. Position forward 1 stores this. Position forward 2 stores this. Skip object includes data member level that stores the highest level for any node currently in the skip list. The skip list stores a header node named head with level plus 1 pointers, where the head level is initially 0 and the level is set to -1 for the empty list. The start of the skip list class follows. Head, level, size, new random, all a random class object. The ideal skip list is organized so that half of the nodes have only one pointer, one quarter have two, 1/8 have three, and so on. So half of them have 2 pointers. Wait, what? Half of them have 2 pointers? Half of the node only one. Oh, sorry, a 1 pointer. Half of them are storing 1 pointer. Quarter of them are storing 2 pointers. Yeah, 25 is storing pointer here, pointer here. 58 is storing pointer here and pointer here. A quarter of them are storing 3. One quarter, half 2, 1/8 plus 3 and so on. And ideally, the distance would be equally spaced. In effect, this is a perfectly balanced skip list. Maintaining such balance would be expensive during the normal process of insertion and deletion. Key to skip list is that we don't have to worry about any of this. Whenever inserting a node, we assign it a label. The assignment is random using a geometric distribution yielding a 50% probability that a node will have 1 pointer, 25 that a node that it will have 2, and so on. Warning function determines the level based on such a distribution. Once the proper level for the node has been determined, the next step is to find where the node should be inserted and link it as appropriate at all of its levels. Here is an implementation for inserting a new value into the skip list followed by visualization. Let me see the visualization. So we insert 10. Now we update array contains all highlighted nodes that are point to the new key. Then insert 30. Update array. The null 30. All of the pointers are now updated. Insert value 20, assuming random level returns 22. The random depth of the node to be inserted is 2, so we must adjust the depth of the header node before inserting. Starting from level 2 of the head, we look for the first node whose pointer points to the largest key that is less than or equal to key 20. So largest is 10, which is less than or equal to 20. Save it into a temporary update array at index level. Okay. If no such key exists because the pointer is null, then update array will contain the last node at that level. We save this highlighted node into our updated array since it will point to our new key 20 if their height matches. The update array actually contains a pointer to the node, but we will display the value of the node it is pointing to. Continue the process, we reduce level by 1 or stop if there are no more levels. Compare 20 to the next record, 30. If what it points to is less, we move forward, else we store this value in the update array. We save this highlighted node into our updated array, and since it will point to a new key 20 if their height matches. The update array actually contains a pointer to a node, but we display the value of the node it is pointing to. Compare 20 to the next record, 10. It is less, we move forward. Now our update array contains all the highlighted nodes that will point to the new key 20. Update, insert value 25, assuming random level, return 0. We are inserting 25. Starting from level 2 of the head, we look for the first node whose pointer points to the largest key that is less than or equal to 25. So over here, it's 20. To the next record, 20. So we store 20 over here. 30. We compare to the next record, 30. What it points to is less than, we move forward. So 20, 20, 20. We save this highlighted node in our updated array since it points to a new key 25 if their height matches. Now our update array contains all the highlighted nodes that will point to the new key 25. This key is to be inserted into the middle, so we must update both its pointer and the node before it at each level. But what about this though? Shouldn't 20 have 2 and not? Okay, there's null over here, so I think that's fine. The remove function to insertion in that the update array is built as part of searching for the record to be deleted. Then those nodes specified by the update array have their forward pointers adjusted to point around the node being deleted. So 25, search for 25. Are these values correct? Now 20. Let's remove 20. HD 20, 10. Oh, the previous value is 10. Now, oh, so the previous value is going over here. Right, so this is the update array. Null, there's nothing here. So yeah, the header. Null and null. No, the header before null is header and before null over here is 10. Of course, 10, HD, head, head, head. A newly inserted node could have a high level generated by random level or low level. It's possible that many nodes in the skip list could have many pointers, leading to unnecessary insert cost and yielding poor data and performance during search. Because not many nodes will be skipped. Conversely, too many nodes could have a low level. In the worst case, all nodes could be level 0. Will it lead to a recurrent linked list? If so, search will require theta in time. However, the probability that performance will be poor is quite low. There is only one chance in 1024 that 10 nodes in a row will be at level 0. The motto of probabilistic data structures that a skip list is don't worry, be happy. We simply accept the results of random level and expect the probability will work eventually in our favor. The advantage of this approach is that algorithms are simple while requiring only theta log n time for all operations in the worst case. For a skip list of size n, the expected memory usage is 2n. This is because a level L node needs n plus 1 forward pointers. It occurs with a probability half to the power of L plus 1. So a skip list is expected to have L plus 1 to the power over 2 to the power of L plus 1 pointers, which is 2. Thus, the number of pointers needed by both BSD and the skip list are expected to be the same. In practice, the skip list will probably have a better performance than a BSD storing the same data. The BSD can have bad performance caused by the order in which the data are inserted. Example, if n nodes are inserted into a BSD in ascending order of the key values, the BSD will look like a linked list with the deepest node at depth n minus 1. The data inserted over the life of the BSD could be randomly ordered. The probability distribution for the cost of insert and search operations would be similar to that of the skip list. Problem for the BSD is that this randomization does not happen in fact, but rather the BSD is constrained by the actual order of inputs and searches. In contrast, the skip list performance does not depend on the order in which values are inserted into the list. In a sense, the data are randomized automatically as part of the skip list probabilistic behavior when the depths of the nodes are selected. As the number of nodes in the skip list increases, the probability of encountering the worst case decreases geometrically. Thus, the skip list illustrates a tension between the theoretical worst case and the rapidly increasing probability of average case performance. All right. So I will end the stream here. How much is left? I will end the stream here then. And yeah, I will start studying the next chapter, next stream. Anyways, see you guys next time. Bye.